Hello, today we're going to talk about UV-Vis. In this lecture, we're going to review hybridization. We're going to develop the particle in a box model. We're going to use this model to predict the location of the peak absorbance of conjugated dyes. Unfortunately, this model won't perform fairly well, so we're going to discuss failures of this model and how to improve this model. This semester, we won't be performing the experiment, but I'll discuss the experiment and instrumentation. Hybridization. Hybridization is a mathematical procedure in which the standard atomic orbitals are combined to form new atomic orbitals called hybrid orbitals. These hybrid orbitals are a weighted average of the standard atomic orbitals combined. The number of orbitals is conserved. That is, the number of atomic orbitals added together always equals the number of hybrid orbitals formed. The goal of this procedure is to develop the lowest overall energy for the system. sp3 hybridization. In this case, we're going to hybridize 3 p orbitals and 1 s orbital to create 4 sp3 hybrid orbitals. Again, these 4 sp3 hybrid orbitals are a weighted average of the unhybridized atomic orbitals used. In this case, since we're using 3 p orbitals and 1 s orbital, the 4 sp3 hybrid orbitals will have 25% characteristic s orbital and 75% characteristics p orbitals. sp2 hybridization. In this case, we're going to hybridize 2 p orbitals and 1 s orbital to produce 3 sp2 hybrid orbitals. Notice we have one unhybridized p orbital. This unhybridized p orbital may be used in double bonds, as shown later. The geometry of sp2 hybrid orbitals. Notice we combined an s orbital, a px orbital, and a py orbital. Notice the px orbital is on the x-axis, and the py orbital is on the y-axis. As mentioned before, the hybrid orbitals are a weighted average of the unhybridized orbitals used. Thus, these 3 sp2 hybrid orbitals are in the xy plane. Okay? They form a planar system. This can be seen in formaldehyde, H2CO. In this case, consider the central carbon. Here we're going to hybridize an s orbital and 2 p orbitals to form 3 sp2 hybrid orbitals. We're left with 1 unhybridized p orbital. Consider sigma and pi bonds. In purple here we have 3 sigma bonds. Here, this is end-to-end overlap between an sp2 hybrid orbital and an unhybridized s orbital from hydrogen. That's the same here. Okay? Over here, we have the hybridization of, the sigma bond of 1 sp2 hybrid orbital and 1 unhybridized p orbital from the oxygen. Again, this overlap, this side-to-side overlap is a sigma bond. Sigma bond, sigma bond. Now, in these cases here, we also have an unhybridized p orbital. They are going to overlap end to end, or side to side. Okay? The combination of a pi bond and a sigma bond yields a double bond. These are single bonds, these are double bonds. Notice this overlap here, okay? This side to side overlap. This pi bond has less overlap than this sigma bond. The pi bond is weaker in general than the sigma bond, okay? But the double bond, the combination of 1 sigma bond and 1 pi bond, is stronger than a single bond, which is just 1 sigma bond. Okay, so now let's talk about our first molecule, DTC, okay? And how we can develop a model to attempt to predict the peak absorbance of this system. All right, so now we have a double bond here, 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 here. Each of those double bonds consists of 2 pi electrons. This nitrogen has a lone pair, okay? That lone pair is roughly in the plane of the pi bonds, okay? So we're gonna consider those 2 lone pairs as part of our conjugated system. These 2 s atoms have these s atoms have 2 lone pairs. One of the lone pairs is roughly in the plane of conjugation. The other lone pair is not. Now, if you would look at an electronic structure calculation, the molecular orbitals you see for the HOMO-LUMO are spread out over the entire molecule, okay? So we're gonna try to develop a model that restricts the electron from this point to this point over the whole length of the molecule. You may read elsewhere that a model can be developed to restrict the electron from the nitrogen to the nitrogen, okay? But the delocalization of electrons is shown by electronic structure over the entire molecule, okay? Okay. Now, we're going to develop this particle in a box model, okay? So consider this model here, okay? Consider these walls here go to infinite potential, okay? Try throwing a ball over a wall. If the wall is infinitely high, you can't get the ball over the wall, okay? That's the same analogy here. This model predicts that the wave function at this point here and the wave function at this point here go to 0. There's no probability of finding the electron outside this well here, okay? So our boundary conditions, the wave function at x equals 0, consider right here, is 0. And the wave function at x equals L, say right here, is equal to 0. Now, that introduces our first flaw in the model in using this model to approximate our system. Let's go back a slide. Now, we have this delocalization of some electron density. And in the slide we just saw, I say, okay, at this point here and at this point here, the wave function goes to 0. There's no probability of finding any electron or electron density beyond this point here and this point here. Well, you know that's not true. There is certainly some probability of finding electron density out here and some probability of finding electron density here. What we won't discuss, but a potential improvement to this model is using a particle in a finite well. We won't discuss that in this lecture, but that could potentially improve this model. All right, so we have this model. Now, let's consider the Hamiltonian. The Hamiltonian is an operator that is the sum of the potential energy operator and the kinetic energy operator. In our case, the Hamiltonian is only going to be kinetic energy. Since there is no potential inside the box, let's go to the previous slide. Again, the potential at the walls go to infinity here and here, but inside here, there's no potential, okay? 0 potential. All right, so that's our justification. And thus, this right here is our kinetic energy operator, minus h bar squared over 2m, second derivative. And since this portion here is 0, our Hamiltonian just becomes the kinetic energy operator. So this operator is going to operate on some function, in this case our wave function. Okay, so we have the Hamiltonian operating on the wave function, gives us some constant, in this case energy, times the wave function again. Okay, so all I do over here is our Hamiltonian, which is our kinetic energy operator, operating on phi is equal to energy times phi again, okay? That's just this here again, except I just divided by minus h bar squared over 2m, okay? Keep this in mind, okay? In the next slide, I'm going to take this term here and move it to the left side, okay? I'm just adding this term here to both sides, okay? I then replace the 2me over h bar squared with k squared. Thus, my differential equation becomes the second derivative of some function plus a constant squared times the function again. So before we even consider this general solution, think about if this makes sense. What function do you know if you take the second derivative of it, it becomes itself again, maybe modulated by some constant? Well, a sine or a cosine, okay? If you take the second derivative of sine, it is sine again times the derivative of this twice, okay? So this is an appropriate general solution for this. However, this won't be the solution to our system because we have to apply the boundary conditions. Remember, our boundary conditions are that the wave function goes to 0 at the left and right endpoints at psi 0 and psi of L, okay? Let's consider the first boundary condition. The wave function goes to 0 at 0, okay? That mandates that the cosine term, the constant in front of the cosine term, becomes 0. Let's scroll back and see why. Okay, we're back here. Psi of 0 equals 0. So we have 0 equals, what is sine of 0? 0. So psi equals 0 plus cosine of 0 is 1. So 0 equals 0 plus C2. So that means C2 has to be 0. So we're left with psi of x equals C1 sine k of x. So then our second boundary conditions means that psi of L equals C1 sine KL, okay? That has to be 0. So we're left with C1 times sine KL equals 0, or sine KL equals 0. When does sine KL equal to 0? Well, at integer values of pi, that mandates that KL equals n pi. I don't have you in front of the lecture, so I can't ask you if that makes sense, but let's review it in case it doesn't. So again, let's just quickly review. We have this general solution to this differential equation, okay? The first boundary condition, psi of 0 equals 0. That mandates that C2 is 0, okay? Because this term here would be 0, this is 0, and cosine of 0 is 1. So we're left with 0 equals C2, so C2 equals 0. Our next boundary condition, psi of L equals 0, okay? So that means psi of L equals 0. So we have 0 equals C1 sine KL, okay? So we're left with C1 sine KL equals 0. Divide by C1, we're left with sine KL equals 0. When is sine KL equal to 0? That happens when KL, that argument of sine, is integer values of pi, okay, n pi. So that means KL has to equal n pi. Okay, so previously, I'll remind you, previously I defined k squared as 2me over h bar squared, but we found that KL is equal to n squared. Solving for E, we have E is equal to n squared pi squared h bar squared over 2ml squared. Okay, great. Or if you don't want to, if you want to write it like this without the Planck's constant divided by 2 pi. Okay, great. Now, n is the energy level. Consider a change in energy level. Say we're going from the nth energy level to the n plus 1th energy level. Okay, so delta E is E of n plus 1 minus E of n. Okay. Simply use this, or this one if you want, but let's stick with this one for now, okay, and plug it into here, okay, and simplify. So delta E is h squared over 8ml squared 2n plus 1. but I don't want it in terms of energy levels, since I don't know how many energy levels there are in my system, but I will know, or I do know, how many pi electrons there are in my system. Each energy level can have 2 pi electrons. Let's just give you an example. Let's say everything's filled, including the 5th energy level, okay? So that would be 10 pi electrons, okay? In terms of n, if I have 2n energy levels, then I have n pi electrons. Example, if n is 5, then I have 2 times 5, that's 10 pi electrons, okay? So in terms of pi electrons, I have my delta E, my change in energy, is h squared over 8ml squared, n, number of pi electrons, plus 1. So in the manual, I give you the length of the system, and you can look up the mass of an electron and Planck's constant, okay? So based on the number of pi electrons, you can get the change in energy level from the nth energy level to the n plus 1 energy level, the homoluminal gap. Okay, let's figure out how many pi electrons there are in our system, okay? So we know each double bond has 2 pi electrons, 2, 4, 6, 8, 10, 12, 14, 16. The nitrogen has 1 lone pair. This lone pair is in the plane of conjugation, okay? So that's another 2. Each of these sulfur atoms have 4 lone pairs, 2 pairs each, okay? One of these lone pairs is roughly in the plane of conjugation, while one of these pairs is away from the plane of conjugation. So we consider one of those lone pairs on each of the sulfur atoms, okay? So 2 electrons each, 2 pi electrons each. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 pi electrons for DTC, okay? The only difference between these molecules is that in each, the primary difference in each of these is that we gain 1 double bond each. So we have 22 pi electrons, 24, 26, 28 pi electrons. Okay, so what are we going to do? The first thing is we're going to calculate the change in energy. Okay, very simple. So delta E is this with 22, 24, 26, 28 pi electrons, okay? We're going to calculate the change in wavelength. We just calculated the delta E, but delta E is hc over lambda, so you solve for lambda. The experimental, and you're also going to calculate the experimental change in energy, okay? You look at your data, or the data I provide for you, and you find the peak absorbance, and again, delta E is just hc over lambda, okay? So now, this is a good time to talk about this. This model for this system will perform poorly. You'll get errors around 20 to 40%, okay? So why is that? Let's go back here, okay? So I just went back one slide. Again, one of the reasons is that the wave function is certainly found beyond the molecule. It certainly doesn't go to 0 here, and it certainly doesn't go to 0 here. There's some probability that you can find the electron density outside this region here. Not only that, this is a one-dimensional model. So it assumes all the electron density is along this line here, this imaginary line that I just drew with the pointer. Certainly not. Look at the electron structure calculations, and you have a smear of electron density. Of orbitals. So an improvement would potentially use the particle in a 2D box, okay? So something like that. And that would be much more reasonable, okay? Okay. So now, just quickly, the procedure. Even though we're not going to perform this experiment this semester, you still may want to know. You sign into the computer, you turn on the device, you wait a little bit because it has to warm up. I have the icon in the center of the screen, double click on it, okay? Then what you're going to do is you click Create New Spectroscopy Application icon, okay? Click Active Acquisition, Okay, then click absorbance and next. Okay, set the integration time to 250 milliseconds, okay, and scans to average to 2, then hit next. Now, at the bottom, you'll see a little box that says turn on the lamp. Click turn on the lamp. If not, you won't get anything. Okay, now you're going to do you're going to do a reference and a background. The reference is your cuvette with just the solvent, okay? Put the cuvette in the instrument, okay? Now there's a kind of a light bulb. You click on the light bulb, okay? And then this will save your reference, okay? The next screen, the light bulb is dark, okay? So you're gonna take the little black cuvette, the piece of wood, and you put it in the instrument, okay? And you click on the dark light bulb, okay? And then wait a couple seconds, okay? Then what you're going to do is you don't have to do that every time. You just change your sample. I have the 4 samples ready for you. You just start with DTC, put it in, you see your spectrum, you hit save. You take that one out, you put the new one in, you see the spectrum, you hit save, so forth and so on. Okay, great. One question I have is to get the concentration of the DTC. Okay, so how do we get the concentration? How do we get the concentration based on our data? Well, our data will give us the absorbance, okay? We know the transmittance is the intensity of light that's transmitted divided by the intensity of light that's incident on the sample, okay? Now, the absorbance of light, we know, is some function of the concentration. The more concentrated the sample, the greater it absorbs. The path length that the light goes through, that makes sense. The greater the path length, the more molecules the photons may be exposed to, and thus the greater absorbance. And the molar absorptivity or extinction coefficient of the species. Okay, that's basically a constant. Okay, so we have absorbance is equal to epsilon times the concentration times length. Okay, so you look at your data. I'll show you it in the next slide. You get the absorbance. In the manual, I have the molar absorptivity, and I have the path length. It's 1 centimeter. If I didn't put that, it's 1 centimeter. Okay, so then you just solve for the concentration in your sample. Your data. Again, I have this data for you. Just make attractive graphs. Here's some somewhat attractive graphs. Okay, so you have your wavelength in nanometer versus your absorbance. You have your DTC, which is yellow, and then you have your red species, your blue species, and your green species. Okay, so in your lab report, make an attractive graph. Okay, safety. Again, always wear gloves. The dyes are somewhat toxic and carcinogenic. Always wear goggles in any laboratory settings, and don't dispose of the samples when you're done. We will be reusing them. Okay, this will save the chemicals. It'll save time, and this is more environmentally friendly. Okay, thank you.